Hello! We have a problem that deals with the complementary slackness conditions of an LP and its relation to the optimal solutions. We let P be this linear program. The first thing that we will do is to write down the dual of P. And we just follow the rules for taking duals, and this is what we have. Next, we will write down the complementary slackness conditions for this primal dual pair. Recall that CS conditions have the form of either a variable is 0 or its corresponding constraint is tight. This goes for both the primal and the dual. Also, we ignore the equality constraints as they are already tight. So, we have 3 CS conditions here. Either x1 is 0 or the first dual constraint is tight. Either y1 is 0 or the first primal constraint is tight. And either y3 is 0 or the third primal constraint is tight. We now move on to the third part. Here we have 3 vectors for x bar, and we want to know whether or not each of them is optimal using feasibility and CS conditions. Here is the logic that we will be using to determine if it is optimal or not. We first suppose that x bar is optimal. Then, by the strong duality theorem, there must exist a y bar that is optimal for D. Then, by CS theorem, x bar and y bar must satisfy all CS conditions. We try to use these conditions to derive a possible y bar. If we find a contradiction, then no such y bar can be found. Therefore, x bar cannot be optimal. If we can derive some vector y bar, then we will need to double check that feasibility and CS conditions are satisfied before concluding that both x bar and y bar are optimal. Also recall that CS conditions are more useful in implication form. That means that if a variable is not 0, that implies that the corresponding constraint is tight. Or, if a constraint is not tight, then the corresponding variable must be 0. We start with the first vector, -3, 1. We can quickly check that this vector is feasible for P. We now suppose that y bar is a vector such that x bar y bar satisfy all CS conditions. For the first condition, we see that x1 bar is not 0. So that implies that the first dual constraint must be tight for y bar. For the second condition, we see that x bar satisfies the second constraint with equality. So this condition is already satisfied. For the third condition, we see that minus x1 bar plus 2x2 bar is not equal to 1. So that constraint is not tight. That implies that y3 bar is equal to 0. Now we also need y bar to be feasible. In particular, it must satisfy the second constraint in the dual. And now we have 3 equations for the 3 entries of y bar. Solving this gives us y bar is equal to 530. Now, just because we have a y bar here does not imply that it is optimal. We still need to check that y bar is feasible and all the CS conditions hold. And indeed they are. So therefore, x bar is optimal for P by CS theorem. We now quickly go through the same process for the other 2 vectors. For our second vector here, it is feasible for the primal. And for CS conditions, x1 is not 0 implies that the first dual constraint is tight, The first primal constraint is not tight, so that implies that y1 bar is 0. The third primal constraint is tight, so this CS condition is satisfied. We also need feasibility for y bar, and now we can solve for y bar, which is 0, 4/3, and 5/3. We see that this violates the constraint that is y3 bar less than or equal to 0. So y bar is not feasible. So, no feasible y bar satisfies CS conditions with x bar. That implies that x bar is not optimal. For our third vector here, we see that it is feasible. x1 bar is non-zero implies that the first dual constraint is tight. First primal constraint is not tight implies that y1 bar is 0. The third primal constraint is not tight, so y3 bar is 0. Combining these three equations give us y2 bar is equal to 1/2. But we also need a feasibility condition for y bar. So having this equation where y1 bar and y3 bar is equal to 0 give us that y2 bar is equal to -2. But y2 bar cannot be 1/2 and -2 at the same time. So this is a contradiction. Therefore, x bar is not optimal. And that completes our problem.